In this video, we're going to take a look at VSEPR theory and how we can use VSEPR theory to predict the geometry of a molecule. So let's start off with, what does VSEPR even stand for? Well, it stands for valence shell electron pair repulsion. So what does that mean? Well, essentially, we're looking at pairs of electrons in the valence shell of an atom. And the repulsion part means that those electron pairs want to stay as far apart as possible to minimize the repulsion of their negative charges. And so molecules will take on different geometries and different structures in order to maximize the distance of these electron pairs away from each other. So we have several different sort of geometries that we need to go through and explore. And what we're going to do is we're going to look at the geometry. We're going to look at what that geometry is with the electron pairs, what it then becomes in terms of the molecular shape, and how to draw it for chemistry. So let's start out with taking a look at two groups that are attached to a central atom. So these are things like, if we draw our central atom as, say, for example, the element A, then it would be two things attached to it, and I'm just going to call those X. So we're doing this very, very general. This is for a compound AX2. So its electron domain geometry, we would say, is linear. And we'll see why in a second. So these molecules always have two bonding pairs of electrons. So they form two bonds, and they have zero non-bonding electrons. So in terms of its geometry, these actually also take on a linear shape. So the molecule is linearly shaped. It has a central molecule, and it's very flat in terms of its structure. So it has a central atom, it has two bonds, and to maximize the distance there, it's 180 degrees away from each other. So that's how we do the drawing. Very, very simple for two electron domain geometries. Now, one thing to kind of note is the molecular geometry is also sometimes called the VSEPR shape. Okay, so this is the actual geometry that the molecule takes, and the electron domain geometry is kind of what it's based off of, its central sort of structure. So what do I mean by that? Well, let's take a look at the three groups attached to an element, a central atom, because this can start to get a little bit more complicated. So the first one we're going to take a look at is if we have a central atom and we've got three things attached to it. So an example might be BF3. The electron domain geometry here is called trigonal planar, and we'll see why in just a moment. It has three bonding pairs and zero non-bonding pairs. Its VSEPR shape is also called trigonal planar. And the reason for this is because those electron pairs, again, want to be as far apart from each other. It's planar because it's all within one plane, and trigonal because it's a triangle shape. So each of these bonds are 120 degrees away from each other, okay? And everything's flat. The other shape, the 3-1, there's another one where we only have two things bonded, so, and one lone pair of electrons on it. So this, again, this sort of shape is based on a trigonal planar, but it has two bonding pairs and one non-bonding pair. And so this shape is actually called bent, or it could also be called V-shaped. Okay, so essentially it looks like the one above, except now we've got just two atoms attached and we have one lone pair of electrons. Now, lone pairs of electrons take up a little bit more space than bonded pairs do. So instead of 120 degrees between these two bonds, it's a little bit smaller at 117 degrees. So the electron domain geometry is based on the same trigonal planar shape, but the actual VSEPR shape name depends on whether they've got the lone pair of electrons or not, on whether it's called trigonal planar or whether it's called bent. The next electron domain geometry we're going to look at is for 4 total number of groups. So we can have 4 things attached to a central atom, and there's 3 sort of combinations we're going to take a look at. All of these shapes are called tetrahedral, and we'll see why in a moment. So they are all tetrahedral. The first combination, we have 4 bonding pairs, no non-bonding pairs. So its VSEPR shape is also called tetrahedral. Let me see if I can spell that right. Okay, tetrahedral. There we go. All right, so in this shape, those 4 things bonded to a central atom want to be as far away from each other as possible. So a little hard to picture in terms of 3-dimensional shapes, but the 3 atoms on the bottom are basically forming kind of a triangle like a pyramid. So we're going to have one in the planar. This top one will also be planar, but to show the other 2 are at angles at the bottom there, we use what we call wedges and dashes. So we're going to draw one with a wedge and one with a dash line. Okay, so that sort of says those wedges are things that are popping out of the page, and the dashes are things that are going back behind the plane or behind the page, whereas the solid lines are indicating those that are in plane with the page. So it gives you a 3-dimensional sort of variety. Now, all of these are all separated by 109.5 degrees. So each of these bond angles are 109.5 degrees. So that is, again, maximizing the distance away from one another. Now, the next sort of variation we have is 3 bonding pairs, 1 non-bonding pair. This shape is called trigonal pyramidal. Pyramidal. So the way I remember it is it looks like a triangle, but it's shaped like a pyramid. So we've got our central atom with a lone pair of electrons, replacing this one here. And then we draw the rest of it the same as the other. So we've got one coming out of the page, one going back behind the page, and one in the plane of the page. Now again, those lone pair of electrons take up a little bit more space. So these bond angles go down to 107 degrees. All right. The last one, we've got 2 bonding pairs, 2 non-bonding pairs. This one's also called a bent shape. It's a bit different than the other bent shape we did though, because now we have our central atom. We've got 1 and 2 x's. At this point, they're in the same plane as each other, because now we only have 2. And then we draw those electron pairs at angles to each other, just to kind of emphasize that it is based on the tetrahedral shape and not on the trigonal planar shape. These bond angles are 104.5 degrees. All right. So that is our electron domain geometries for 2, 3, and 4. In the next video, we're going to take out electron domain geometries for 5 and 6. So they get a little bit more complicated. So that's it then for this video. We'll see you in the next one.